So good morning, everyone online and in the room, and welcome to this 22nd Envecon Applied Environmental Economics Conference. I am Ozdemiroglu. I'm the CEO of EFTEC and co-founder of UK Network for Environmental Economists, who is bringing this conference to you. I have a few words of welcome before our keynote speaker, Emily Shuckburgh. We have a lot of new friends joining us this year as presenters, as delegates and supporters. And this is wonderful for us because the success of a long-running event series like this depends on new blood joining. So thank you for being here. But also, we have a lot of old friends working in environmental economics for a long time. And this mix of old and new is particularly important at this time where the popularity of environmental economics is increasing very rapidly. There are new clients who are seeking our advice and finding everything we do new, exciting, but also challenging. And many of these clients are pushing boundaries in their work, changing perceptions of nature and impacts and dependencies of their policy areas and businesses on nature. And I must mention, it being the International Women's Day, that at least I see a lot of women leading such change, and I'm very proud to acknowledge that today. Whoever we are, whatever stage of career we are in, it's up to us as practitioners to ease the decision makers' concerns and nurture their excitement about what economics can offer to solve environmental problems. And more importantly, to acknowledge that we don't talk about nature only when we cause a problem, but appreciate it as the foundation of society and economic activity. And when I say practitioners, I don't just mean those with degrees in economics. I know that there are many of you here and online who are experts in other disciplines and who are using or wanting to use economic evidence to support your work. You're all welcome to be part of ACNE. Share the common cause of making nature visible and powerfully visible when economic policy and business decisions are made. We stand at the crossing points of many, many disciplines. Our job often involves linking the conceptual to practice, the sciences into economics and finance. And that's why it gives me great pleasure to invite our keynote speaker this year, Professor Emily Shuckburgh, who has an amazing cross-disciplinary expertise and practice. She is the director of Cambridge Zero, the major climate change initiative at the University of Cambridge, where she's also professor of environmental data science. Among many other things, she is also the honorary president of the Aldersgate Group, of which EFTEC has been a proud member for a long time. Emily will talk to us about climate science, that's featuring heavily in this year's agenda, about what we should know and perhaps about what she expects us economists and other practitioners to contribute. Emily, welcome.
Thank you very much, and thank you for inviting me to give this talk as well. As Ece said, I'm Director of Cambridge Zero at the University of Cambridge, and I'm also Honorary President of the Aldersgate Group, which is actually an amazing alliance of businesses, but many other organisations that are all working together to look to support progressive solutions associated with climate, nature and broader environmental issues. What I thought I would do today is really three things, I think. One, I was going to give you a little bit of an update on some of the climate science side of things, particularly because at a global scale, the climate is in particularly extreme state right at the moment. So I thought I'd give you a little bit of an update on that. Then I thought I'd try and draw out what I think some of the key aspects of the climate science that are most relevant for economics and economic thinking might be. And then finally, I was going to give you an example of a project that I'm involved in that's taking a genuinely transdisciplinary approach, and where actually exactly the comments that you've just heard about economists really being, if you like, at the hub of being able to connect together different disciplines is actually absolutely central to that project. So I thought I'd highlight that as an example as well. So let me start off though with the global picture associated with climate change. So I thought I'd better start off with global average temperatures, which many of you might be aware of, have been in an exceptionally extreme state over the last year or so. You can't actually see very well, I don't think, up there. I think it's not come out very well on the screen, but below that, there's the sort of the mean of the last 30 years or so is the zero line, and 2023 is, you can see clearly, is the orange line. It was about 1.45 degrees warmer than the pre-industrial level. This is an El Nino period, and about 0.2, we think, 0.2 degrees of that additional warming is a contribution from the natural El Nino cycle. But nevertheless, that still means that even if you discount that in terms of the long-term mean, we're around about 1.25 degrees above the pre-industrial level. I don't know whether any of you were watching, read any articles over the last couple of days, but February of this year was 1.77 degrees above the pre-industrial value. So we're really getting horribly close to that 1.5 degrees threshold. That's in terms of air temperatures. The other thing that's possibly even more extreme at the moment is sea surface temperatures. So again, you can't see very well, there's lots of light grey lines that you can't see very well on this projection, but you can see the mean over the previous 30 years or so. And then you can see quite how extreme 2023 was and how much even more extreme 2024 has been. And again, in part, those high temperatures are due to El Nino, but El Nino really only affects the sea surface temperatures in the Pacific. And so in terms of global surface temperatures, this reflects a really strong increase in global sea surface temperatures. And from the climate science perspective, this aspect is not well understood at the moment. It's a surprise that sea surface temperatures have been quite so high over the last year and a half, and that's an area of active research. And it has pretty strong implications, actually. I spent a decade working at the British Antarctic Survey, particularly studying the polar regions. These sort of really high sea surface temperatures obviously have strong impacts on the ice sheets, because a lot of the melting of the ice sheets is occurring because the warmer waters are encroaching underneath the ice sheets and they're melting from below. So there's a strong knock-on impact of that. So then focusing on the polar regions, I've got just two other images that I wanted to show you of just quite how extreme things are starting to become. The first one is in the Arctic sea ice. This is a trend that's been continuing over the last more than 30 years now, of a strong decrease in the amount of sea ice in the Arctic. What you're seeing here is the extent of sea ice in September. So what happens in the Arctic is that ice grows, the ice extent grows over the winter, and then slowly melts each year over the summer, and so it reaches its minimum extent at the end of the summer in September. So this is when you see the minimum amount of sea ice each year. It's decreased in area by almost half over the last 30 years, and you can see in particular the last decade has seen exceptionally low levels of sea ice in the Arctic. Overall, the Arctic is warming at about 4 times the rate of the rest of the planet through a set of different feedback effects that particularly affect the polar regions. So that's the Arctic, but what's the really unusual thing of the last 2 years is that the Antarctic has started to see really significant sea ice loss as well. So Antarctic is exceptionally cold, so to get actually to the level at which you start to melt ice in the Antarctic takes quite a lot of warming. But also the Antarctic is fundamentally different to the Arctic. So the Arctic, in simplistic terms, is an ocean surrounded by land, and the Antarctic, in simplistic terms, is land surrounded by ocean. And so in terms of the physics that occurs in the two polar regions, it's really quite different. And the fact that the Antarctic has this ocean surrounding it almost isolates Antarctica in a dynamical sense from the rest of the planet, and has meant that in some respects it's been somewhat protected in a way from the warming that's happened elsewhere. But what you can see in the last couple of years is there's been really dramatic sea ice loss in the Antarctic. And again, that's been a surprise. It's not totally understood from the scientific perspective yet why we've seen such a decrease over the last couple of years in Antarctica. And there's always a concern with any of these things, as I'll come on to describe in a moment, from a scientific perspective, that some of these, when you see a dramatic change, that it might be crossing some sort of tipping point into a different state of the climate system. So there's a lot of interest at the moment in understanding what's happening in Antarctica in terms of sea ice. And then I thought I'd just do, just a couple of other aspects just to finish off that discussion of what's happening at a global scale. This is the emissions of carbon dioxide over the last few decades with the 2023 projections for carbon dioxide emissions shown. But what I really wanted to highlight, that's the emissions, but what obviously matters most for the climate is the actual concentrations of those greenhouse gases in the atmosphere. That really steady increase continuing in terms of the carbon dioxide levels, now reaching 420 parts per million, something that certainly when I started my career as a climate scientist was inconceivable that we would ever reach those limits, but we have, and you can see it's very much still on a dramatic, well, pretty much straight line actually going upwards. But the other one that's of significant concern, and again, there is uncertainty in terms of understanding exactly why this is. You can see methane strongly increasing. There was a stabilization in the early 2000s through a combination of different factors, the demise of the Soviet Union, regulations associated with landfill sites and so forth. But we've seen this dramatic increase in recent years. The concerns are that in part that may be a feedback effect as we're seeing the warming of tropical wetlands, for example, or potentially even the release of methane from the frozen stores of methane in the Arctic, and that therefore it's a feedback effect associated with climate change itself in part. So let me just turn then to future projections, and this is where I want to start to bring out some of the aspects of the climate science that I think are particularly pertinent for then interfacing with the economic modelling. These are some images from the last IPCC report. I've particularly highlighted global surface temperature change into the future and sea level rise. The key aspect that I wanted to highlight here is that under the lower emissions scenarios in IPCC, the temperature levels off. So there are scenarios in which temperature broadly is Paris Agreement compliant and stays broadly below 2 degrees of warming with an almost below 1.5 degrees of warming. And by the end of the century, the temperature levels off. But the key point that I wanted to make was even in those scenarios where you see a levelling off of temperature, sea level rise still continues to increase, and increase a long way into the future. And so what you're seeing on the right-hand side of this plot is the projected sea level rise for 2300, because the sea level continues to rise for centuries into the future. And even on that lowest emission scenario, which is the blue band, you see very significant sea level rise out for centuries into the future. And the important implication of that is that many of the responses to climate change, and sea level rise as an example, are non-linear. And they're not non-linear in the same way with respect to different variables. And so if you try to characterize the climate response simplistically in terms of a simple damage function, then you're going to be missing a huge amount of the impacts because so many of the different aspects of climate change respond in different ways. This is an example where you've got an acceleration of sea level rise long after temperatures have stabilized. There are many other examples, and I was just mentioning a potential one, where you might pass tipping points and create linearities in that sense. So understanding that nuance is incredibly important for understanding the risks and impacts of climate change. The IPCC, this is another IPCC figure, but I've actually conflated two different figures. One is the IPCC figure, and then the other one is from Carbon Action Tracker, looking at global pledges and actions associated with climate change. This has been, on the left-hand side, a diagram that's been part of the IPCC reports for the last 3 cycles of IPCC reports as a way of summarizing and synthesizing all the evidence around climate change in a simple diagram, which is sometimes called the burning embers diagram, or the reasons for concern. And there are these 5 categories that get brought together to create this diagram. And what it shows is, with increasing temperature on the vertical axis, the level of risk across these different, assessed risk across each of these different categories, with the lowest risk being yellow and then rising up with temperature. One thing to note that is really important is that if you look at successive IPCC reports, the level of assessed risk in these diagrams has been increasing. So there's a significant increase in the level of assessed risk in the 6th assessment report compared to the 5th assessment report. But I thought I would just, using the Carbon Action Tracker's analysis of where global response is in terms of policies and actions, I thought I would just draw a line across so that to highlight that. So this is where we are today. In terms of where we're at high risk, unique and threatened systems, so this would be things like coral reefs, which we know are already very exposed and vulnerable to precisely those extreme sea temperatures that I showed in an image a moment ago, as well as to the increase in acidification of the oceans. So some areas of the planetary system are already at high risk. If we look across the Carbon Action Tracker's estimate of the most optimistic scenario in terms of if all global pledges were implemented, has end of century temperatures around about 1.8 degrees of warming. Those unique and threatened systems then enter into high risk. But we also enter into high risk on some of these other categories, in particular extreme weather events, which of course we're starting to see playing out around the world already. And then if you look actually at Carbon Action Tracker's estimate of current policies and actions, then you see that all these categories start to move either into high or very high risk. And the category that I want to particularly highlight on this one is what the IPCC rather opaquely calls large-scale singular events. And that is essentially the potential for passing tipping points in the climate system. So let me just give you a little bit of a sense of what some of those potential tipping points might be. And here are just 4 examples. On the top right is an example that I've already mentioned very briefly. That white circle that you can see is actually a bubble of methane coming out of a lake in the Arctic. So there are vast stores of frozen methane in the land, in the permafrost, in lakes in the Arctic, and at the bottom of the ocean. And the concern is that as the Arctic warms, that methane may be released into the atmosphere. And methane is a much more powerful greenhouse gas than carbon dioxide. So that would be a strong concern in terms of a feedback effect. On the top left-hand side is an image from the Amazon rainforest. There was actually a very big synthesis report that was just published last week with the latest assessment of the state of the Amazon rainforest. That combination of climate change and deforestation and deliberate or induced wildfires is causing real concern that the Amazon in the coming decades may tip between being a rainforest and being a much lower tree density environment. And so there's very significant concerns about the Amazon passing a tipping point. And the bottom 2 images are from the 2 polar regions. On the left-hand side, Greenland. On the right-hand side is Antarctica. And the integrity of the ice sheets, both in Greenland and in particular in West Antarctica, although to an extent in East Antarctica as well. There's real concerns that as the world warms, we might pass the threshold at which those ice sheets are stable. There are already concerns actually that they may have already passed the limit at which of their stability. In Antarctica, there's a glacier called the Thwaites Glacier that sometimes is called the Doomsday Glacier, and there's there's been a huge amount of study of that glacier in recent years, with strong indications that it may already be in irreversible retreat. And this is an example where we know, if we go into the distant past, when the world was warmer than it is today, but not significantly warmer, that those ice sheets were not intact, and sea level was between 6 and 10 meters higher than it is today, which would, of course, have a globally devastating impact. So then, non-linearity, key thing to account for in terms of climate, but also the potential of passing tipping points. And then there's a set of other aspects that I wanted just to highlight briefly in terms of other key aspects associated with climate that have implications in terms of these being fundamental characteristics of the climate system. So the first is that climate-related risks are highly networked, correlated, interconnected. The example that I have up here is of the Panama Canal on the top left, which is seeing extremely low water levels at the moment, which is causing global implications, not least in terms of supply chains, which are critically dependent on the Panama Canal. In part, those extremely low water levels are due to El Nino, but that's been exacerbated by climate change almost certainly as well. And just one example of where you can start to get global related risks, but you need to understand those interconnections in order to be able to properly assess those risks. The second example I have on the top right is of cascading risks. This is an image from British Columbia in 2021. There were really extreme temperatures in the summer in British Columbia, almost reaching 50 degrees Celsius, and extreme wildfires that resulted. But that also then resulted in parched land that when it came to the autumn, there ended up being very severe floods because the water wasn't able to drain away on that very parched land. So you start to get these cascading risks. That's a very common occurrence associated with climate change, and one that you clearly need to take account of if you're properly to assess the risks. Starting to understand the risks beyond the meteorology itself and the secondary impacts, and then the tertiary impacts beyond that is also really, really central. And the example that I have on the bottom left was, I think, a surprise to many. This was back in last summer when the first case of transmissible dengue fever was identified in Paris, and then there was a mass fumigation of one of the arrondissements in Paris as a consequence. Dengue fever is starting to spread throughout southern Europe as the conditions are becoming more amenable to the spread of the mosquitoes that transmit that particular disease. Understanding the health impacts of climate change has been really rather slow to be adopted as an academic discipline, but just one of many examples where that interdisciplinarity and transdisciplinarity is really central to understanding climate-related risks. And then the final example, and I could have many others on here as well, is around geopolitics. So starting to try and understand geopolitical risk, not just associated with the direct impacts of climate change, but also associated with the response to climate change, is starting to be something that is increasingly recognized as being critically important. This is nickel mining in Indonesia. Just one example where actually a transition to a low carbon economy, in particular a switch between having a heavy oil and gas driven global economy to something that might be much more dependent on resources such as nickel and the different geographical dimensions associated to that, just one of the ways in which geopolitical risk starts to become really prevalent. What I wanted to do in the last couple of minutes is then just take you back to just highlight some of the aspects of current research on the climate side of things, climate science side of things, that interfaces potentially with the economics side of things. The first example of that I wanted to give is associated with AI. So as in every other discipline, AI is starting to become really prominently used in climate science. This is the first project that I was involved in a couple of years ago now, where we've first really implemented machine learning approaches in climate science. It's a model that we developed to project Arctic sea ice extent using data-driven approaches. Since then, we've been starting to roll out the use of AI AI and machine learning across many different aspects of climate science. But where I think it has a real potential is helping to interface between the climate modelling and economic modelling, and to better connect the two different modelling approaches so that we can potentially start to include in our economic modelling some or more of those characteristics that I was describing in terms of the non-linearities and the tipping points and the thresholds and so forth that are associated with the climate science, and all the non-linear interconnections and interfaces with different related risks, whether that's in terms of health or geopolitics, etc. So that's one area where I think there's huge opportunities. The other aspect that I wanted to talk about was this idea that economists can be absolutely central to transdisciplinary approaches to problems. And I wanted to give you an example of a project that we have been undertaking now. It's coming up for 3 years, just entering the 3rd year in Cambridge, funded primarily by the Natural Environment Research Council. And this is very much to undertake whole systems analysis of landscapes. There are 3 landscapes in particular that we're working in the UK: the Fenlands of East Anglia, the Cairngorms in Scotland, and the Cumbrian Lake District. What we are looking at is how those landscapes could potentially be managed differently for the benefit of climate and nature, but critically also the people who live and work in those landscapes. The entire project has been, in a really genuine way, co-designed from the start between academics from across the university in Cambridge. We sometimes joke that literally every department, from archaeology to zoology and everything else in between, are involved in the project. So academics from across Cambridge, but also really critically practitioners and stakeholders. So it's a genuinely transdisciplinary approach. It's been incredibly exciting and successful, but quite genuinely, economists are absolutely central, because they sit in between the people who are working on the science side, where we're taking greenhouse gas measurements or biodiversity measurements, and the people who are working on the social anthropology side of things, who are working deeply within communities and connecting together the information from across those different dimensions to start to create a really rich description of how those landscapes could be managed differently, is absolutely centrally important, and a way of bringing together all the different data streams. And just to give you just a little bit of more of a richness on just one of those landscapes, the one that we've been working most on to date is the Fenlands around East Anglia. The challenge here, the image that you can see on the left-hand side is greenhouse gas emissions from land use. Fenlands in East Anglia are a huge amount of peatland. It was all drained in the 17th century, and so there's large peatland. That peatland is emitting large amounts of greenhouse gases when it's intensively farmed, and actually the peat itself is steadily eroding away, so it's an existential risk for the farming community in any case, because they don't have any peatland left. 30% of the peatland has been lost just over the last few decades. Major biodiversity issues, very little of the original wetland left. Major questions in terms of the greenhouse gas emissions. Substantial percentage of UK greenhouse gas emissions come from peatland emissions. Huge challenges in terms of water, both too much water because it's very low lying and at risk of flooding, exacerbated by climate change, but also too little water. It's one of the driest parts of the country, and there's large amounts of housing development in particular that's allocated and planned for the region. But then at the same time, there's huge economic questions. The rural economy is absolutely central to the economy, contributes £3 billion per annum to the local economy. And so just simply not farming the area any longer is clearly not going to be a viable solution. It's also very important nationally in terms of a significant amount of our food crops are farmed in East Anglia. But there's also huge social inequalities. And if you look at any of the inequality indices, then this Fenland region, and actually the two other landscapes that we're interested in the UK, feature heavily in terms of the most deprived parts of the country. So we have this huge set of different issues that we need to collectively understand, and collectively understand very much through the lens of an economist, and understanding how to integrate the different disciplinary expertise into that framework is central to what we're trying to achieve with the project. So I hope that's given you a little bit of a sense both of the global picture, where there's an interface between climate science and the world of economics, but also where we could potentially all be working in a transdisciplinary way to help develop solutions for climate and nature and for people. Thank you.
If there are one or two questions, if you wanted to take, Emily, if there are any questions for Emily, observations? Matt and Alistair. Just wait for the mic, Matt.
Hi, Matt Georges. I'm self-employed economist. Can you give us any good news at all, do you think?
You know what, actually, I think that that last project that I just described is a bit of a good news project, because I think we've started to make some progress on it that, often, I'm sure there's quite a few people from DEFRA in the audience, often the farmers are at war with the conservation groups and also at war with DEFRA and the Environment Agency. There's a lot of tensions between those different communities. And I think that just the fact that we've started to get trust and dialogue between those different sets of people, and starting to think through what potential solutions that everyone is invested and engaged with. There are always trade-offs, of course, but if we can get to a state where people think that they've been part of developing the solutions and the solutions are fair, then I feel that we can actually make progress. And I think just with the, even though we're now only just entering our third year of the project, I think we've made significant progress associated with that. Might all go horribly wrong, but at the moment we've managed to put our blue helmets in and go into quite a contested landscape, and I think have reached a point where we've got good dialogue between the different groups. So if that can be replicated at scale, then maybe there is hope.
Thanks. Alistair Johnson, one of those people from DEFRA. On that last example that you gave, have you taken a natural capital approach? And if so, has it delivered any insights as to how to engage with the local communities and stakeholders?
Yeah, I mean, we've actually sort of taken multiple different approaches. Probably the most fundamental element that we've been trying to do is really start off from a systems thinking perspective. And even in that context, the transdisciplinary aspects of it have been interesting. So we brought together people from our engineering department in Cambridge who have, long-standing view of systems and taking systems analysis. But then we had people from the conservation community who were part of the project, who for decades have also been doing systems analysis, but they turned out to be quite different in their approaches of how they do it. So we've now been trying to work out how we bring that together. And so although natural capital accounting is definitely a stream within what we're doing, in some sense, the bigger framework actually is the systems analysis. And as part of the systems analysis, it's as much about identifying the needs and interests at all the different stakeholders, which can be quite broad, and then identifying within that where the key barriers for, or opportunities for interventions are. So it's a slightly different framing in a way from the natural capital accounting comes into it, but it's not quite as central as it might otherwise be. Anyway, happy to talk further.